So let's see what is actually mean by a permutation group. Okay, let's see the definition. So a permutation of a set A is a function from A to A, that is a bijection. Okay, that is a bijection. So what do you mean by bijection? It is 1 1 and onto. Okay, so let's see one example. So you take A is equal to 1 2 3 4, then let's define a bijection sigma from 1 2 3 4 to 1 2 3 4 like this. As 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4. So let us write it is in this fashion. Sigma, write the set A on the top, and below you write the elements which is mapped. So 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4. So this is the basic notation of a permutation. So permutations are bijections. So you know that how many ways you can permute for numbers. We already studied this. So number of ways to permute 4 elements is 4 factorial ways. Okay, and we denote Sn to be all permutations with n elements. So how it will be the cardinality of this set, number of elements in set will be n factorial. So this Sn contains all the permutations. In set notation you may write it this sigma from A to A, where sigma is a bijection and size of A is equal to n. So this is one way notation. So all bijections are from A to A with n elements. So we can see that if you are given a function, two functions, the best operation we can see is the composition. Okay, so given two permutation sigma and gamma, we can perform the composition. We already studied what is composition, right? So let's see what is mean by that. So let's take two two permutation sigma and gamma. So let sigma be 1 2 3 4 and 3 2 1 4, and gamma be 1 2 3 4, which map it to differently to 1 3 4. Okay, now how do you perform the sigma dot gamma? So let's do it is in a normal way. So sigma dot gamma is again a function from A to A, and sigma dot gamma of 1, it is sigma of gamma of 1, which is sigma of gamma of 1 is 1 goes to 2 na, so we can write it is 2. Okay, now what is sigma 2? Sigma 2 is again 2. So that means 1 goes to 2 in sigma dot gamma. Okay, so this can be observed in a different fashion also. So here in the notations, the basic notation, you can see 1 goes to 2, and once you hit 2, you start that value from the sigma, then 2 goes to 2. That means 1 goes to 2 also. So let's check whether it works in other where 2 goes in that. So 2 goes to 1. Now here 1 goes to 3. So 2 goes to 3. Let's check whether it is correct. So find sigma dot gamma of 2. This is sigma of gamma of 2. Sigma of gamma of 2 is 1. Sigma 1 is equal to 3. So we find that 2 goes to 3. Similarly, let's try where 3 goes to. So 3 goes to 3 here. Once it hits, start from the left side. 3 goes to 1. So 3 goes to 1. Okay. Now what is 4 goes to? 4 goes to 4 here. Here 4 goes to 4 here. So 4 goes to 4 itself. So how do you write sigma gamma or sigma dot gamma? It is 1, 2, 3, 4. Now map everything. 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 4. So you got it. So let's compute one more in this fashion. Like let's take another symbols, theta. So theta will be 1, 2, 3, 4, 5 will take 3, 2, 4, 1, 5. So now let us be again we take something like omega. So omega is another permutation on 5 elements. Let it be 1, 5, 4, 3, 2. Okay, they are different, right? So let's find out what is theta omega. What I mean by is theta dot omega. Theta dot omega, first you write the set as simply 1, 2, 3, 4, 5. Now you observe the other one. This way you will understand what exactly doing. So 1 goes to 1. Okay. Now start from, so 1 hits here. So start from here. So 1 goes to 3. So totally 1 goes to 3. Now 2 goes to 5. 5 goes to 5. So 2 goes to 5. 3 goes to 4. 4 goes to 1. So 3 completely goes to 1. Now 4 goes to 3. 3 goes to 4. So 4 goes to 4. 5 goes to 2. 2 goes to 2. So 5 goes to 2. So this is the answer you get. So I think you understood how I am calculating this numbers. Okay, you don't need to do calculate this particular operation again. This simple trick will explain how to do that. Okay, so this is basically you find the products. Now we will introduce another notation, and for this, that is what we call the cycle notation. Cycle notation. So cycle notation is simple. So let's took one. Uh, so let's take this as 35142. Let's try to draw the graph of this function. So for the graph, these are the elements 2, 3, 4, 5. Okay. Now you can write. So let's try to map from the permutation. So 1 goes to 3. Okay. Now 3 goes to 1. So that actually completes that cycle. Okay. Now let's start from 2. So 2, so I'll draw 5 somewhere here for the convenience. Now 2 goes to 5, and again 5 goes to 2. What about 4? 4 goes to itself. So here you can see there are exactly three different components, you can say, right? So this is one component, this is another component, this is another component. So in cycle notation, this sigma can be equivalently, you can write like this: 4 1 goes to 3, that is the meaning. 1 3, this is 2 5. So you can write, you can avoid this 4 also, because it is 4 goes to 4, that is a simple thing. If it is only one element, you can avoid that. Then 1 3 2 5 you can write. This is actually equal to any one of this. You can, it can be 3 1, it can be 5 2, or you change only one. So all of them are equal because of the cyclic nature of this, right? So they are same. Even if you write the first thing is here, it is here, no problem, because in the graph you can see wherever you draw the graph there is no change. So this is one type notation. So I'll give you one more example um, which will give you more understanding about this notation. So let's look at again a bigger one, a 7 permutation. 1 goes to 2, 2 goes to 3, goes to 4, 4 goes to 6, 5 goes to 7, 6 goes to 2, 7 goes to 1. So let it, this is be a permutation, right? Now we'll try to capture what is actually going. So sigma can be written as, you don't have to draw the graph all the time. You start with one element. So you know, 1 goes to 2, then 2 goes to 3. Okay, so first where it is goes, so 1 goes to 2, right? So that you write in the right side. 1 goes to 2, again 2 goes to 3, now 3 goes to 4, now 4 goes to 6, now 6 goes to, oh yeah, you should not use 2 because already 2 is used. So what is left is you have to, 6 goes to 6 itself, like, no, what is left, 2 3 4 5, I think. Okay, 5, 6 goes to 5, now 5 goes to 7, 7 goes to 1, yeah, 7 goes to 1. So 1 is another number is repeat, the first number repeats means you have to stop. 7 goes to 1, so it is a full length full length. Okay, there is no gaps, you can say it's a full length, 1 2 3 4 5 6 5 7. That's what happened. Now let's see one more, maybe you can see the difference. So 3 2 4 5 7 6 1. So let's look at this one. So how do you write? So you start from 1, no, nothing is repeated, right? Yeah. So 1 goes to 3, 3 goes to 4, and 4 goes to 5, 5 goes to 7, 7 goes to 1, so you stop, and 6 goes to itself, right? This is another kind of cycle notation, right? So yeah, let's see one more, then we will stop. So theta, you can try by 7 2 2 goes to 2 1 9 6 then 4 7, like, okay. What about this? How do you write this? So 1 goes to 2, 2 goes to 3, then 3 goes to 1, so you close it. Now take other number which is not in the first cycle. Let us be start from 4. So 4 goes to 5, 5 goes to 6. Now 4 goes to 5, 5 goes to 6, 6 again goes to 4. So we close. 7 goes to 7. So here you can see 3 different cycles. So here 1, 2, 3 and 4, 5, 6. Okay. Now note that cyclic permutation. So this is actually equal to this, no problem. You can write like this also, no problem. Also you can write the cyclic permutation. For example, 1 2 3, the same 1 2 3 we will notate this also. You can write cyclically, you can permute 2 3 1, no problem. So you can write 2 3. So I'll tell you generally. So this 1 2 3 is same as 2 3 1, which is same as 3 1 2 and 1 2 3. We again use cyclic. So what I am doing is 2 3 I write first, then I write 1. So 2 3 1. Now 3 1 and I write, then I write 2, like that. So cyclically you are permuting. So what is actually happening is the graph of all of these are same, because 1 goes to 2, 3 2 goes to 3, 3 goes to 1. So they are all, everyone is equal. Similarly 4 5 6. So I'll give you one more cycle with the 4 elements, maybe 4 5 6 7. So this is actually equal to 5 6 7 4, actually again equal to 6 7 4 5, again equal to 7 4 5 6. Then you repeat 4 5 6 7. So why they are all equal? Because if you draw the graph 4 5 6 7, all the graph of all these cycles are same. So cyclically permuting will be same. That's why this is, you can written as this fashion also, no problem. They are all same. Okay. So this is the idea of cyclic notation. Now if you given two permutation in cyclic notation, how do you multiply? Okay, multiplication in cyclic notation. Multiplication using cycle notation. So let's take 2 sigma, 2 permutations. So let it be 1 2 3 4. This is cycle, and let's take gamma equal to 3 2 1 4. They are not equal. Okay, because gamma is not a cyclic of whatever. This is whether they are equal or we don't care. We, how do you calculate it? So okay, listen very carefully now. So what we have to do is we write sigma gamma start 1. So that 1 is starting from here. Now where this 1 goes? So this 1 goes to 4. Okay, now you come to the sigma left hand side. So where 4 goes? 4 goes to 1. So what happens is we started from 1 and closed it. So 1 closes it, because 1 goes to 4, 4 goes to 1. Now that cycle is closed. We cannot do anything. So start from fresh fellow 2. So 2 is here. Start from here. Now what happens to 2 goes to 1. Now where 1 goes? 1 goes to 2. Again you have to close it, because we can't do anything, right? Because if you start from the 2 here, again is 1, 1 goes to, we can't do this. Now start 3. What happens? 3 goes to 2 and 2 goes to 3. So this is basically the getting the inverse of this. So this is identity. This is how it is looks like. 1 goes to 1, 3, 4. You can check this. Who is this guy first of all? Sigma. This is in basic notation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, right? Gamma, this is 1, 3 goes to 2, 1 goes to 4, 4 goes to 3, 2 goes to 1. Okay, then sigma dot gamma in our basic notation, we can see 1 goes to 4, 4 goes to 1, 1. 2 goes to 1, 1 goes to 2, right? 3 goes to 2, 2 goes to 3. Correct only, it is identity. Which, yeah, so they are both inverses. Now let's take something else. Let's take sigma is equal to 1, 2, 3, 4, and gamma is equal to 1, 3, 2, 4. What happens? Let's see. So sigma gamma, start from the left side, 1. Now where is 1 goes to 3, right? 1 goes to 3. Now when 1 hit 3, go to here. So 3 goes to 4. So you write 4 there. Okay, now very important. Don't close it because you didn't reach where you started. You started from 1, now you reach 4, so write 4. Now that 4 you have to start from the right side. Okay, so 4 goes to, now 4 goes to 2. Where 2 goes to? 2 goes to 1. Now you can stop because you reached in a element where already we started. So this is 1, 4. Okay, now start a fresh fellow, 3. 3 goes to 1. Where 1 goes to? 1 goes to 2. So you write 2 here. Now that 2 you start here. 2 goes to 4. 4 goes to 3. 3 is already in the cycle. So this will be the answer. So maybe you can check. So sigma 1, 2, 3, 4. 1 goes to 2. 2 goes to 1. 3 goes to 4. 4 goes to 3. Gamma 1, 2, 3, 4. 1 goes to 3. 2 goes to 4. 3 goes to 1. 4 goes to 2. Do the normal multiplication. 1 goes to 3, 3 goes to 4, 1 goes to 4, 2 goes to 4, 4 goes to 3, 2 goes to 3, 3 goes to 1, 1 goes to 2, 4 goes to 2, 2 goes to 1. So this is same. 1 goes to 4, 4 goes to 1, 2 goes to 3, 3 goes to 2. Both are same. So this is how you multiply in cycle notation. So this algorithm, this idea you have to keep. Okay, so I will finally do a big fellow, then I will stop. So let 3, 5, 7, 6. I multiply with gamma and 3, 4, 5, 7. Okay, so 6 is there, which is if even if you don't write 6, let it be. Anyway, so 1. Okay, let it be 6, 2. Okay, so 1, 2, 3, 5, 7, 6. So let it be 4 because it is a 7 permutation I am looking at. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How do you multiply? So start from here. Okay, very listen carefully. So 1 goes to 3. So 1 you start. Now 3 goes to 5. So you write 5 here. 5 end up here. Start from 5 here. 5 goes to 7. 7 goes to 6. Right. Okay. Now start 6 here. 6 goes to 2. 2 goes to 3. Okay. Now start 3 here. 3 goes to 1. 1 goes to 2. Okay. Now start from 2. 2 goes to 6. 6 goes to 1. So 6 goes to 1 means 1 already there, so you close this. Now what is not in this cycle? 4 is not there, so you start from 4 now. So 4 start, 4 goes to 5, 5 goes to 7, right? 7. Okay, now 7 you start, 7 now goes to 4, 4 goes to 4, so you close. So everyone is there, 1 2 3 4 5 6 7, so done, so complete done. So this would be the answer. So let's so you now you verify with this, right? In basic notation, try to calculate this, you get the same thing. Okay, with that I move to the group SN. So the group SN, so the group SN is simply, SN is a set of all permutations on A with n elements with the composition, it is a group. Okay, so we already studied, if you have any bijection, f dot g dot h is equal to f dot g dot h, so it is associative. Now who is your identity? So identity is a identity function, identity bijection. So what is identity bijection? Everyone maps to the same thing, so I of x equal to x, or what we can say, x maps to x. As an example, 1 goes to 1, 2 goes to 2, 3, or we do write like this, 1 2 3 2 3. In cycle notation you can write either, it is same as anything, or you don't write anything. This is your identity. Now what is the inverse? The inverse part I want to do, I want to give you an example first to find the inverse of sigma. Suppose you have a uh, permutation like this. Okay, so what is the inverse? So for inverse, what you have to do is you just flip this. Okay, so I write flip. What do you mean by flip is just rotate it. So if you rotate, what happens? Write the second row first and first row second, then arrange it. Arrange means the top value 1 has to come first, so 1 3, that column will come second, this column 2 1, third this column 3 2, for that column. Now check whether it is an inverse or not. How do you calculate? 1 goes to 3, first write the number, 1 goes to 3, 3 goes to 1, 1 goes to 1, 2 goes to 1, 1 goes to 2, 3 goes to 2, 2 goes to 3. So it is identity. Okay, so this is the idea, you just flip it, right? So you get an inverse, so every element you get an inverse. So but I will try to prove it more generally. Suppose you have a sigma, so you have 1 2 3 up to n. What is your mapping? Let me call it is sigma 1. If I call sigma 1, you will be, we call sigma 1, sigma 2, finally maps to sigma n, some number, because I don't know that, that's why I'm telling the function value. Now what is my claim is sigma inverse, or I call gamma, just flip it, right? Flip. When you flip, what happens? Sigma 1 1, sigma 2 2, up to sigma n, get n. How to prove that this is a identity? If I can prove sigma dot gamma of any number here, so sigma k's are any k, if this is, you will get again sigma k, I am done. Why? Because every member sigma k maps to sigma k, or x maps to x. So how do you do this? So start from LHS. So your LHS is sigma dot gamma of sigma of k. Okay. So what is sigma of k? No, no, I'm just telling what is sigma. This is sigma of gamma of sigma of k. What is gamma of sigma of k? Here, what is the meaning of this? Here it is gamma of sigma of 1 is equal to 1, right? So similarly everything. So sigma of gamma of k simply k. So we are done. So we started from sigma of k. So sigma of k maps to sigma of k, or x maps to x. This is the same as gamma of sigma. What happens? Gamma of sigma of k. So this is what you get. You get gamma of sigma of k, right? Then because sigma you are taking from 1 now, so this is, you already found that gamma of sigma of k is equal to k, right? From this gamma of sigma only. So here you can also see that k maps to k, or in both case it is an identity function. So gamma dot sigma equal to sigma dot gamma, both are identity functions. That is, uh, gamma is the inverse of sigma. So every permutation has a inverse, that is Sn is a group. Okay, yeah, thank you.